Alright guys, just again to discuss our intermolecular forces, we have LDFs, which is our weakest, dipole-dipole hydrogen bonds, which are stereotypical intermolecular forces, electrostatic, which is also a type of intermolecular force, but it is the strongest type. It is significantly stronger than our hydrogen bonds. And part of the reason for that, remember, hydrogen bonds and dipole-dipoles are dealing with the partial charges due to the difference in electronegativity, whereas electrostatic attractions are dealing with the attraction between legitimate charges, where it's an actual positive and an actual negative, versus the partial positives that you get with the electronegativity, partial positive, partial negatives on the polar molecules. There we go, sorry. We then have our intramolecular, which is our covalent bonds. We have our non-directional, which again means the electrons are being shared in multiple directions with multiple different atoms, versus directional, which is our stereotypical, what we think of like this type of bond right here, is a directional covalent bond between two atoms. The electrons are being shared between two atoms. Okay, so with the intermolecular forces in mind, let's go through and look at our 4 types of solids we're going to discuss. The first type is our molecular solids. So these are what we've already really kind of discussed in terms of solids. So this would be like ice, water as a solid, carbon dioxide, dry ice as a solid, sugar as a solid, bromine even as a solid, Br2, our diatomic. So really what we have to think back to, so remember the lattice structure we talked about where it had the little black circles at the vertex of each of the corners. Okay, and we talked about these could be atoms, molecules, or ions. In this case, what we're dealing with are molecules at the vertexes. Okay, so notice here's our picture of water at the vertex, and notice it's not always necessarily a corner like this. It kind of depends on what the shape is of the lattice structure. We have a water molecule, and the water molecules, of course, are attracted between the oxygen and the hydrogen, because remember, water is H2O, where oxygen is pulling the electrons towards itself, causing that partial negative, and hydrogen has those partial positives, which then are going to be attracted to an oxygen and another water. So if we kind of remember what's going on here, notice that's what we see here. The green lines are representing those hydrogen bonds, our intermolecular forces here, that are holding these together. Notice the fun thing about water, if you guys remember that ice is actually less dense than liquid water, which is a little unusual. Most solids are more dense than their liquids and gases phase. Water is one of those weird exceptions. Just kind of as a fun fact, check out the structure you see here, and it's a little bit hard to see in this picture. You're welcome to pull up another picture on your phone if you want. But notice kind of this hexagonal shape that's going on here. It's kind of a 3D hexagonal shape. That creates this kind of pocket in between the lattice structures themselves, which is that opening that allows for a less dense, more spaced out molecules. So that kind of gives us a lattice structure here. So molecular solids, what holds them together? What is the force that holds our molecules together? Well, it's IMS, and these could be any of the IMS. So these could be IMS, or sorry, not IMS, LDFs, dipole-dipole, are hydrogen bonds. What that means is it depends on the molecule that's being bonded, are being attracted to each other. So here, because it's water, we have a hydrogen bond, versus if I was dealing with a bromine molecule, their attraction, okay, would be an LDF because it's nonpolar. So it just kind of depends on the type of molecule we're dealing with, depends on the type of intermolecular forces. So again, this is kind of a continuation of what we've already discussed. The different intermolecular forces are going to cause a difference in properties. So let's kind of talk about the properties of a molecular solid, because that's actually the important part of this chapter. So the first thing we have to recognize is that because intermolecular forces are the weakest version of forces holding molecules together, or holding species together, is that they have low melting points and low boiling points. So what does that mean? That's in the grand scheme of things. That doesn't mean they all are going to melt or boil below 0 degrees Celsius. It just means in the scope of all the different things we're looking at. So looking at iron, looking at diamond, looking at sodium chloride versus looking at water, they're all going to have relatively low melting points and boiling points. And again, that's because they have those weak intermolecular forces. So kind of as a reminder, what we just talked about, we have LDFs, dipole-dipole, hydrogen bond as our generic normal IMFs, and these are our weakest ones. We then have our electrostatic, and then we have our covalent, both directional and non-directional. So these are increasing in strength as we go down, and therefore these melting points and boiling points are going to be increasing as we go down as well. So LDF, dipole hydrogen bonds being our weakest type, they're going to have the lowest melting points and boiling points. Now keep in mind, and that even takes one step further, our LDFs are going to have even lower boiling points and melting points versus our hydrogen bonds. So again, our bromine is going to have a much lower melting point than, let's say, water, which is hydrogen bonds. So that aspect is still playing a role in here as well. The next thing we have to recognize is they are poor conductors. Okay, so let's just kind of do a little bit of physics here, and I'm not going to do too much. Physics is not my strong point. But what does a conductor mean? Specifically here, we are referring to electrical conductor. Electricity is the flow of electrons. And a very simple term, your physics teachers will probably elaborate on that a lot more once you get into that class if you're not already there. So what allows for a flow of electrons? Well, it's a distribution of charges that allows for the electrons to be able to flow, meaning I have a positive on one side, a negative on another, and I have electrons that are loose or free-flowing that are able to move from a negative charge to a positive charge. Again, that's in a very simplified fashion, if you will. So that distribution of charges being able to flow and then having loose electrons. So let's kind of talk about it here. First off, what we're referring to in terms of loose electrons is we're looking at the force that is holding these particles together. Well, are there electrons in this force? In a manner of speaking, no, there's not. This force is the attraction between a partial positive and a partial negative. There are no electrons actually in this in any way, shape, or form. It's an attraction due to the uneven distribution of electrons within the molecule itself. So these electrons are not loose. They're stuck within the molecule. And then also keep in mind there's no electrons within this bond right here, in this force at all. So electrons are not able to flow in any way, shape, or form. And again, remember, these are partial. They're not full. So what that basically means is there's no ability for electrons to be able to flow. Therefore, they are considered poor conductors. They also have low densities. Again, this is in the grand scheme of things. So this is comparing water with a hydrogen bond, or bromine with London dispersion force, to, let's say, iron, if you will, which is down here with our non-directional covalent, which again, we'll see that in a little bit. So iron is much more dense than water is going to be. Okay, and then the other thing about these is these guys are typically considered soft. What does that mean? Basically, if you think about like your hardness scale, like diamond, it can't be scratched by anything, but it can scratch everything. That's what it's referring to as soft. Not typically something we care about so much in this class, but just something to mention. What we're typically going to be looking at in this class is the melting points, boiling points, the conductivities, and that type of information. Okay, so that's a molecular solid. Okay, all right, let's look at the next one. Next one is an ionic solid. So again, our lattice points or our vertexes here are going to be ions in this case. What does that mean? It means that they're going to be held together by electrostatic attraction, which is where this guy, let's say, is negative, this guy is positive, and these are legitimate charges versus our partial charges, so they're actually a full attraction between them, much like a magnet would be, a strong magnet, if you will. Like think our neodymium magnets, if you remember that conversation we had a few months ago. Okay, so any ionic compound falls into, of course, our ionic solids. And our structures are all going to be different. Your formula unit will actually have the ratio. So sodium chloride, which is a ratio of 1 sodium to 1 chlorine, is going to actually have a different lattice structure than, let's say, calcium chloride, which is 1 calcium to 2 chlorines. And that's kind of the beauty of the lattice structures, and why there are so many is because of the ratios that exist between them. And again, something like aluminum oxide, 2 aluminums to 3 oxygens, would have a different lattice structure as well. Okay, and again, these are being held together by our electrostatic attraction, so these guys are even stronger. So again, I'm just going to keep putting this over here until we kind of get the basic gist of it. We have our LDS, our dipole-dipole, our hydrogen bonds, etc. And then we have our electrostatic and our covalent. So notice that our electrostatic falls kind of in the middle of our generic IMFs, and then our covalent. What that means is they're going to have higher melting points and boiling points than our molecular solids because they are stronger. They are being held together by a stronger force. So again, if we think about melting and boiling are endothermic, meaning they require energy. So because these are stronger, they require more energy to break apart. Okay, these guys are, I'm skipping the brittle, I'm going to come back and talk about that in just a moment. These guys are poor conductors as solids. What does that mean? Again, let's go back and kind of discuss what we talked about earlier. Are there actual electrons in this force of attraction holding it together? No. Are there loose electrons? No. We're thinking ionic compounds are transferring electrons, so there's that idea that electrons might be loose, but not really. Is there a distribution of charges? No, all the charges are actually balanced out because we have the positive, negative, positive, negative, positive, negative back and forth. So as a solid, there's no ability for electricity to be able to flow. However, the minute we melt an ionic compound, these structures basically go to bits. They're no longer in a crystalline structure. They become more of an amorphous. Most liquids are considered amorphous. Are considered not to have a consistent structure anyways. So the positive and negative become a little bit more distributed, at which point in time electrons can flow because there is an uneven distribution of charges. This is why ionic compounds, or not ionic compounds, electrolytes in Gatorade, for example, they're called electrolytes because they're able to produce electricity. And that also is true if I take this and dissolve it in solution. Again, you're going to have that distribution because the ions are going to dissociate, spread apart, and move around in the solution, again allowing the electrons to be able to flow. So ionic compounds are kind of fun where they are not conductors as solid. Again, they don't have that ability to have the distribution of charges or the ability for electrons to flow, but they are again conductors as both a liquid and as in solutions. All right, let's go back and talk about the brittle. Keep in mind, brittle does not mean soft. I know we kind of use them interchangeably, or we may think of them as almost synonyms. They're not. Ionic compounds are, in technicalities, probably harder than our molecular solids due to the strong intermolecular forces, but the problem is you start having this idea of something called cleavage. Okay, which, yes, I know is kind of a funny word, but let me show you what I'm referring to. So we have the alternating charges, and I'm going to kind of show them as best as I can over here. And this is a little bit easier to do when you can actually look at it in class on the board, but I'll do the best I can. Let's say the big ones are negative because there are anions, not always the case, because you can have a larger cation than anion depending on where we are on the periodic table. But let's say that's what we have. So we have our little ones are positive, our big ones are negative. And notice we have this alternating charges. Okay, and I'm only kind of looking at like a piece of it. So let's say I come in with a hammer and I hit this. Okay, and I push this side down in some form or another. So let's see what that turns into. Okay, and again, big ones are negative, little ones are positive for this picture, just so we can kind of see what's going on. So I push this far row down. Notice what happens now is I have two negatives next to each other and two positives next to each other. Well, what is that going to do? Well, I have like charges next to each other, so they are going to repel, and that means these guys are actually going to break off or break away from it. That is what we in turn call cleavage, or breaking. So ionic compounds are considered brittle because of this aspect of the alternating charges, and if those like charges end up being next to each other for whatever reason, they will end up breaking apart. Now, kind of the fun thing as these break apart, they'll break apart into the similar pattern and the same pattern, because remember, this pattern would be continuing right next to it, which is why when you go back to that picture we had earlier, all the crystals have kind of this rectangular squarish shape is because of how they break apart. They're holding on to their pattern. Other thing is these guys have high densities. Again, higher densities. Notice that high and low, and the terms we're using here again are relative. Okay, they're not definitive. Okay, so those are our first two types of solids. I have to stop because we've hit our 15 minutes, and we'll talk about the next two in just a minute. Thanks, guys.